In today's video, we shall look at the rolling motions of rigid bodies. One example of such a motion is a moving wheel on a surface, like that. So it is moving like that and rotating like that at the same time. So a rolling motion for such a body consists of two parts. One is the rotational motion about an axis passing through the middle, and the translational motion of the center of mass. Let's look at the kinetic energy for such a motion. The kinetic energy for such a body has two terms. The first term is half mv squared, where v is the speed or the translational speed. M is the mass of that body. The second term is rotational kinetic energy, which is given by half times ICM omega squared. ICM is the moment of inertia of that body about an axis passing through the center of mass, and omega is the angular speed of the body. Another way to look at this motion is as follows. Such a rolling motion can be decomposed into two parts. The first part is pure rotation about an axis passing through the center of mass, like that, with angular speed omega. And the second part is the translational motion of this body to the right, with a translational speed v. Let's look at the first factor, the rotational contribution. Let's look at 3 points. The topmost point, of course, has a translational speed v. The middle point does not have any translational speed. And the bottommost point has a velocity of minus v, minus because it indicates the direction of the velocity being to the left. Now let's look at the second part, the translational part. The topmost point has a velocity v to the right. The center of mass, which is in the middle, also moving with velocity v to the right, and the bottommost point also moving translationally with velocity v to the right. What that means is, in a rolling motion, the topmost point has velocity 2v, the middle point or the center of mass point has a velocity v, and the point where it is in contact with the moving surface has a zero velocity. Thus, a rolling motion can be viewed as a rotational motion about a moving axis that is passing through the contact point, as indicated. So what that means is we can also write the kinetic energy for such a motion in terms of purely rotational kinetic energy as follows. It is half times the moment of inertia of this body about that axis, let's call that axis O, times omega squared, where omega is the angular speed of that rotational motion. So these are two ways of looking at a rolling motion. To understand this process further, let's look at the following problem. A solid disk is rolling without slipping on a level surface at a constant speed of 5 meters per second. How far can it roll up a 45 degrees ramp before stopping? So what's happening here is you have a horizontal surface, and then you have this ramp like that, and a disk is rolling forward like that and continue to climb upward along that ramp up to a certain height. When it gets to the bottom of the ramp, its speed was 5 meters per second. It will roll up the plane and stop at a certain point. We want to determine that distance that it covers before it comes to a complete stop. Let's call that distance s. We can solve using energy principles. So this is the initial point and the stopping point is the final point. So conservation of mechanical energy says the total mechanical energy at the initial point, which is the sum of gravitational potential energy and kinetic energy, equals the sum at the final point. So the sum of gravitational potential energy and kinetic energy at the topmost point where it comes to a complete rest. We know at the final point its speed is 0 meter per second, so that goes to 0. Now we have the freedom to choose gravitational potential energy to be 0 somewhere. We can take the initial point, that level, to be the level where the gravitational potential energy is 0 joules. So that means that goes to 0 as well. Now let's write down the expression for the kinetic energy. As we have discussed before, it has two terms. The first one is the translational term, half times the mass of that solid disk times the square of that speed, so 5 squared, plus the rotational kinetic energy, which is half times the moment of inertia of a solid disk about its axis passing through the center of mass, is quite simply half times the mass times the square of the radius, times omega squared. Omega is the angular speed of that rotating disk. However, we can express that angular speed in terms of that translational speed as follows: as a translational speed over the radius of that disk. So substituting that expression there, we get 25 over r squared. That equals UF. UF is the final gravitational potential energy. So if we assume the height is h, then we know the final gravitational potential energy is mass times gravitational acceleration times h. Now you see that mass goes away like that. This r squared will cancel the r squared from there, and you can determine the vertical height h. The value for h turns out to be 1.911 meter. But note, we are interested in the distance up the ramp. What we have here is just a right angle triangle. So this is h and that is s. The angle is 45 degrees. So you see, using trigonometry, we know h over s is sine 45 degrees, which is 1 over square root 2. So that means s, the thing that we are looking for, equals square root 2 times h, which is square root 2 times 1.911 meter, and that's going to give you an answer of 2.70 meters for the answer, and that solves the problem. Problem 2. A solid ball, mass of which is 5 kg, rolls smoothly from rest down an inclined plane at an angle of 30 degrees. If the ball descends a vertical height of 1.3 meters to reach the bottom of the inclined plane, find the speed at the bottom. Also calculate the frictional force on the ball as it rolls down the inclined plane. So what you have is an inclined plane like that. The angle is 30 degrees. And you have a solid ball that is rolling like that. It starts from a vertical height of 1.3 meters. We want to know the speed of this ball as it gets to the bottom of that plane. What is that speed? To do part A, we are going to approach this rolling motion in a slightly different way. We are going to look at it as if it is moving about a moving axis like that. The spin of omega, it's occurring about the moving axis, the second picture that we talked about earlier. So the kinetic energy at that initial point plus the gravitational potential energy at that point equals the kinetic energy at the final point plus the gravitational potential energy at that point. It is moving from rest, so that's going to go to 0. If we take the gravitational potential energy at that horizontal level to be 0, then that's going to go to 0 as well. So the gravitational potential energy at the initial point is the mass times gravitational acceleration times 1.3, the vertical height here. And that equals to the final kinetic energy. Now, if we are looking at the rolling motion as if it is moving or rotating about this moving axis, then it is half times the moment of inertia about that axis. Let's call that axis like that, omega squared. So what is the moment of inertia of this solid ball about that moving axis? It is the moment of inertia about the center of mass, which is 2 over 5 times mass times the square of the radius. You can find this in standard tables, plus m times the distance squared. That distance squared is the distance between the axis passing through the center of mass and the new axis. In this case, it is just the radius of that solid ball, so mr squared. We also know this angular speed is connected to that translational speed, as that translational speed v over the radius of that solid ball. Substituting this and that expression in this term, we get 7 over 5 mr squared for that sum, times omega squared, which is v squared over r squared. So that r squared goes away, and this m cancels that m, and you can get your v. Solving for v, you get v to be 4.3 meter per second. So there we have it. The answer for part A is 4.3 meter per second. Now let's calculate the frictional force. Among the forces that are acting on this moving solid ball are as follows. So it has the weight, which we can call it mg. There's a normal force acting like that. There's a friction that is acting in an opposite direction between the ball and the surface of the plane. And of course, let's not forget the component of that weight that is causing it to go down is mg sine 30 degrees. So sine 30 degrees is half. What that means is there must be an acceleration. Let's call it A. That is the acceleration of the center of mass. The friction here is important. This is a static friction that we are talking about, that is ensuring the rolling motion and preventing that solid ball from slipping. So Newton's second law says half mg, the forward force down the plane, minus that static friction must be the same as m times acceleration. So this is equation 1. The second equation is Newton's second law for rotation, which is that the torque comes only from one force, namely the static friction. The weight and the normal force passing through the center of mass will contribute no torque. So they contribute no torque about the center of mass itself. Or to be accurate, they create no torque about an axis passing through the center of mass. So the torque created by the static friction is given by the force static friction times the distance between the axis of rotation that is passing through the center of mass and the force itself, which in this case is the radius of that solid ball, so r. And that equals to the moment of inertia of that solid ball through the center of mass, which is 2 over 5 mr squared, times alpha. Alpha is the acceleration of the center of mass over the radius of that solid ball. So you see all the r will go away, and that would give you the acceleration in terms of friction as quite simply 5 over 2m static friction. Substituting this expression inside equation 1, we can solve for the static friction. So now equation 1 would give you half times mg minus static friction equals mass times ACM, which is 5 over 2m static friction. So m goes away, and you can get the static friction in terms of mass. And that turns out to be mg over 7. Since m is 5 kg and we can take g to be 9.81, the value for static friction is 7 newtons, and that solves the problem. As always, thank you for watching.